6 years ago, a coworker of mine gave a lunch talk titled Misuse-Resistant Code. The talk was chock full of jargon and concepts I was unfamiliar with. Refinement types, contravariants, dependent types. I'd certainly never heard of IDRIS before. I was lost, and as far as I was concerned, this was something for the academics, not me. None of the languages I got paid to write software in could do any of this fancy type system stuff anyway, so why should I care? With 10 minutes left, my coworker wrapped up their presentation with the following demonstration. Our code snippet contains two types, user and authenticated user. If our password is correct, then the user's login method creates an authenticated user. We can then use the authenticated user's logout method to sign the user out, consuming the authenticated user object. By taking self instead of an immutable reference to self, we're able to signal that this method is ending the lifetime of this authenticated user. And note that you can no longer invoke do work after calling logout. Written this way, we've created the following state machine. This example demonstrates the power of the type state pattern. The type state pattern allows us to express the state of an object in the type system. Notice that while we have two distinct types, we're really just talking about the same user. The only differentiation is on whether that user is authenticated. It was with this demonstration that I realized that Rust could be the future for secure software development. For those who don't know me, I'm Nathanial Lattimer, aka Donut. I'm both a software and security engineer, a hacker with plenty of bug bounty and security research experience, and a Rustation of about 6 years. As a security engineer, one of my primary interests is in identifying practical ways to holistically address security problems. And with the previous demonstration my colleague gave, I began to see Rust as one of those tools that we could use to shift security left, stopping vulnerabilities before they even got to the code review stage. The code we just reviewed is a simple example of leveraging type states to create misuse-resistant code. And while the authentication and session management are critical parts of any non-trivial application, I felt compelled to explore other big problem areas that could be addressed using this approach. The Open Worldwide Application Security Project, that's a mouthful, or more commonly referred to as OWASP, maintains a list of the top 10 security risks to web applications by analyzing broad trends in the industry. The current OWASP top 10 identifies broken access control, the thing that enforces authorization, as the most important risk to web applications, and has regularly noted broken access control or some variant thereof since at least 2007. It's important to understand the distinction between the two. Authentication, often abbreviated authn, deals with establishing a verifiable identity for a party, whereas authorization, often abbreviated authz, concerns itself with what your identity, attributes, and relationships say about your capability to perform some sort of action or access a resource. So in other words, authentication is who you are, and authorization is what you're allowed to do. The challenges associated with building effective access control are not simple. Before we try and change things, let's take a quick look at what the state of the art is today. Well, to start with, a vast majority of applications implement some or all of their access control manually via ad hoc control flow. This includes if statements, early termination of loops, throwing exceptions, and the like. Basically, anything you can do to break out of the process that you're in, the control flow that you're in. This ad hoc hopes and prayers strategy to implementing access control logic is unreliable. In some ways, it's no different than relying on developers to check a buffer size before writing data into it. And as much as I want to have confidence in that code reviews could catch these issues, access control is especially difficult to review. It requires a deep understanding of the product and the expectations of its users. It's hard to catch things that aren't present in the code but should be. Where code reviews fail, tests try to pick up the pieces. Tests are an industry standard practice to helping ensure quality, minimize bugs, and communicated the intended behavior of the code you just wrote. And I'm sure many of you write tests for your software, or at least I hope so. Unfortunately, in practice, tests aren't effective at preventing security issues. The reason being is that developers are very eager to write tests that validate their code does the thing they intended it to do, also known as positive tests. But developers infrequently implement the associated negative tests. These are the tests that validate that when things go wrong, the software operates within spec. These are the kinds of tests that would catch an unprivileged user being able to access a resource that doesn't belong to them. Thankfully, some libraries exist that make access control a little easier to understand and implement. Django, for example, has a whole permission system built into it. This allows developers to easily attach permission classes to a view, restricting the actors that are able to access that view. It can even be extended to object-level permissions and custom permission implementations by developers. This gives developers great control over the security of the APIs that they're implementing. Another solution which feels very appropriate to share, given that this is a Rust conference, is OSO. OSO is an authorization as a service platform that aims to help developers move away from the ad hoc control flow logic that we talked about earlier. It allows developers to create definitions for actors, resources, and the policies that constitute your access control. Also, OSO put up this really great blog post titled "Why Authorization is Hard," and it covers some of the challenges that we're talking about here today, but plenty more. So go give it a read if you have a chance. Now, some of you may have heard of Google's authorization system, Zanzibar. A whole paper was written about it. It's pretty impressive technology. But there's also these spin-off open source solutions like SpiceDB or OpenFGA. These centralized authorization systems, which includes OSO, work by enabling organizations to define their access control policies separately from their business logic. Organizations then stream data points, or as they're referred to as facts, to these centralized authorization systems so it can evaluate policy decisions on the fly. These facts could be anything. Common examples could be new users signing up, newly created resources, or updated role assignments. Eventually, when an organization needs to make an authorization decision, it issues an API request to one of these centralized authorization systems, which asks if the specified actor with the given resources should be able to perform the requested action. And since these centralized authorization systems already have all the facts and your policies, these requests are pretty easily satisfied. Solutions like this are great because they help with standardizing access control patterns, and they also make those access control patterns really reusable within your team. If all I have to do to make my code secure is a single API call, that's very replicable. But re-implementing a bunch of control flow logic that's scattered about and intermixed with my business logic, that's very difficult and takes a lot of time and intuition and experience to kind of develop. It also helps call attention to the currently configured access control for a given API endpoint. It's super easy to look through the code, find the one API call, and understand the access control requirements of this endpoint. But when we go towards the manual ad hoc control flow logic, it's scattered everywhere, and it can take an investigation to figure out what's even going on. Centralized access control makes integration easy because most of your endpoints are only going to require a single call. Or if they're taking multiple, you may have a modeling problem. There are a few drawbacks, though. For example, within permission systems like Django's, inheritance can actually obscure the configured access control. I've seen this problem occur quite a lot, and it makes figuring out what the effective policy is on any given endpoint kind of difficult because it can be spread amongst serializers, views, and parent classes. Secondly, not everybody wants to send data over to a third-party hosted service. I mean, I certainly wouldn't. Now, sensitive information isn't necessarily required to be sent, and there are self-hosted solutions, But in the world of microservices, especially in a data store per service group model, this can be difficult to set up, having to make sure all of those services are streaming data and not falling behind to your self-hosted centralized authorization service. It also doesn't necessarily enforce that the data in question, the data used to answer your authorization query, is the data that's used afterwards to perform an action. This can lead to insecure direct object references, or IDOR. You also have to remember to check the access control. Now, good software design can help accommodate this issue. Sometimes you can place those checks in middleware. Sometimes the platform like Django can handle it for you. And some client libraries will help handle this problem for you as well. But it can go, it goes without saying that mistakes can still happen. And lastly, access control logic usually doesn't actively respond to changes in your implementation. What do I mean by that? Well, I think it's really important we discuss it. Imagine that your organization implemented an endpoint that generated a report about a user's team. This endpoint validates the user's authentication, determines what team they are on, and then gathers the non-sensitive data that they will inevitably render and place in a PDF. Thankfully, this was relatively easy to implement because we added view-based permissions and they did a lot of the work for us up front. At some point, the summer comes around and your team got an intern. Their first task, update the report generation. You see, the admins have been asking to see billing information in their reports. The information is sensitive, and so it should only be viewed by the admins. Now, the correct implementation would be to check if the user was an admin and optionally include that information in the report. However, because the intern is working on an old, infrequently used feature, they accidentally added this information to everyone's report. A simple mistake anyone could make, but one we've probably all seen happen in production before. Just that really silly bug that slips through all the cracks. So what happened to our permissions? Well, they actually worked. They did exactly what we designed them to do. They ensured that our user was authenticated and they were a member of the team that they wanted the report for. The problem was that this authorization requirement didn't change with us when we fetched billing information for the team. Some frameworks do have field-level access control, which could help here, but that might not be enough depending on the complexity and the functionality that you're implementing. The questions that you may be answering could be a little bit more complex than field-level access control. All right, so we have a pretty good idea of what authorization looks like in the real world, and we've got a pretty good idea of the kinds of solutions that are out there already. So let's try our hand at designing a system that might be able to improve on the status quo. So I think two major areas that we can address are the areas that I want to focus on: making authorization more reactive. So the way we're going to do that is by placing access control on functions, and this should help us. This should help change the access control requirements as we start invoking different functions within our code. If I suddenly call a new function, I will be subjected to the access control requirements of that function. Secondly, it should help enforce that the correct authorization logic is checked. So if an endpoint is accessing sensitive data or performing some privileged operation, it should be impossible to forget the check. Could we leverage Rust's type system to avoid these problems? And as a quick disclaimer, this is more of an exercise in what is possible with Rust rather than this is how I'm recommending we do this all in the future. If you want a good solution for your production environments, I'd recommend one of the aforementioned approaches or whatever makes sense for your use case. We're going to use unstable Rust features that require the nightly compiler. So this approach is more of a production to zero rather than a zero to production, if you get what I mean. Okay, with the disclaimer out of the way, let's discuss some of the goals. We're going to provide a mechanism to define the access control policies on functions. We're going to support attribute-based access control. And if you haven't heard of that term before, you've probably implemented it. Most systems tend to fall under attribute-based access control, even if they claim to be role-based access control, which you're probably more familiar with. A good example of ABAC is ensuring that your account is enabled and your account is a member of a team. These are attributes on your actor, and that's kind of the whole shtick. We just check that you have all the prerequisite attributes and then grant you access. And third, we are going to try to provide a semi-usable experience. Okay, so imagine for a moment that user and authenticated user type state at the start of this talk. If we consider that do work function as the sensitive function and our login function as the authorization check, then we could see that a type state could actually be used to demonstrate that the developer performed the authorization check ahead of time. But this is a trivial example. We need to be able to support multiple attribute checks that can occur in any order, and including extraneous ones that aren't even relevant to the questions we're asking of the principal in the current state. With typical handwritten type states, or even using many type state libraries, this could be pretty tedious to map out. To support this, we're going to want some sort of collection within the type system. And I don't mean a vec, I mean something that happens at compile time. That way we can just add a type that attests to the fact that we've invoked that function and performed the appropriate authorization check. Then, if our type-based collection contains all of the required attestations, it would implement a trait, and it gave it access to the protected function. Thankfully, there is such a concept, type lists. Using type lists, we can keep track of types themselves, allowing us to do compile time trickery. A basic type list might look like the following, and if this looks familiar, it should. It's a linked list. However, with this structure, we can create a compile time list of types by nesting node within itself. And for those wondering, this is similar to like an H list or heterogeneous list if you've seen this before. But the distinction is that we're not storing data alongside the different types. So using our type list, we can construct a list of types that looks like the following. Very nasty, I know. The type list contains the following three types, attribute A, B, and C. So the presence of each of these types is intended to attest to the fact that we must have previously called the associated authorization check, because that is the only way that we can create these new types. Here's an example of what one of those attribute check functions could look like. So for the body, we can imagine implementing anything you want in there, anything you might find in an if statement. User.is_enabled, or user is member of some team. We can pass whatever arguments we need into it. But what matters is when it succeeds, we return a brand new node that contains the current one and also has an attribute attesting to the fact that this function succeeded. If we implement our attribute check methods a bit more generically so that terminal can use them too, then we can create type lists in the following way. Now we have a type list that carries with it proof that we've run these three methods at least once. Note that the type list that we're working with is heavily simplified. It doesn't keep track of which objects hold this attribute, and we'll touch on that in a bit. Now that we have this type list, we can implement our protected function on our type list. Does anyone see a problem with this approach? Couple of hands, great. So I think the big glaring issue is if I call one of these attribute check methods out of order, then I suddenly can't call this protected function anymore. And even though in a vast majority of these cases, the order in which we run these checks shouldn't matter, doing it this way is going to cause us problems. So what I really want to be able to do is ask the following question of the type list. Do you contain this attribute somewhere inside? Well, this is where things get a little less pretty. So we need a way to tag our type lists with something we can easily check at compile time. A good candidate for this are traits, as trait bounds provide a nice enforcement mechanism for our type states. We'll implement the trait so that even if the attribute is all the way at the bottom, like the color blue here, The outermost entry will also implement the same trait, has blue. So in this diagram, the outermost red entry implements has blue because deep inside the node's entry, a blue entry is found. And it also implements has green and, of course, has red. So from the outside, we see all has color. Okay, so let's create the trait implementations to do this. We define our has attribute type, very similar to has color. And we then try to implement, we do two impl blocks here to try to ensure that the attribute inside of the type list is surfaced to the top, as well as the most recent entry. However, there's an issue here. This code won't compile because we have conflicting trait implementations. By show of hands, how many of you have encountered the conflicting trait implementation issue before? A lot of hands. I have great news. Come to the dark side, we have unstable. So let's visualize a type list that contains red twice. We can see that for both of those entries, separate impl blocks are affected, which means that we have two conflicting implementations causing the error. And Rust C is trying to be nice here. If we actually defined a function here, then it wouldn't know which function definition to use. And so it's stopping us from making a potential mistake. But in our case, we're not trying to use functions. We're just trying to tag it like some metadata. Google gets away with it, why can't we? Thankfully, Rust has an experimental feature, marker trait adder, which gives us access to marker traits. So if you've never heard of these before, marker traits allow multiple overlapping implementations on the same type. The main caveat is that we're not allowed to add a function or associated type to our trait, but that's fine in this case. We're just using it to add metadata, right? So here's that same trait implemented from earlier, and note the only difference is that we just added the marker annotation on top. Simple. Awesome. Now that type list from our previous example implements the following traits. And now that we've been able to tag our type list with these traits, we can talk about the contents of our type list within trait bounds. So the last step to all of this madness is implementing a trait containing the function we're trying to protect. And then we implement that trait on any type that satisfies our conditions. In this case, we want to ensure that callers have called the check attribute A, check attribute B, and check attribute C functions. And we do that through the has attribute A, B, and C. Now, if we want to invoke the guarded function, this protected function, it's as simple as calling those check attribute functions a number of times in whatever order you like, and then simply invoking the function. And if we remove one of the checks, we get the associated compiler error. And it's relatively helpful, too, given the madness underneath. Clearly, we just haven't checked attribute B. And with another small change, we can actually start support passing this object around and building up access control checks as we go. We could imagine a middleware doing some initial checks, and then your endpoint satisfying the rest of them. In a way, it feels a little similar to Go's context object here. Now, to make this more developer-friendly, we can start to add a few derive macros so that we can generate the necessary traits, trait bounds, and impl blocks. We can also try to expose a nicer API, something a little bit more human-readable. Unfortunately, due to lack of time, we're not going to be getting into derive macros here. I know you're all very excited. But the good news is that I built a library that does this, and so much more. So if you're interested, Daiquiri is a library that lets you define easy-to-read policies for functions, custom attributes, and goes way beyond what we discussed today. So for example, Daiquiri can strongly tie the attribute attestations to the specific instance of objects used to validate those attributes. This way, when you validate some condition, you're assured that the objects that you're using afterward to perform that action were the same objects that were used in that attestation. Policies in Daiquiri follow a standard actor action resource syntax. So it makes it pretty easy to review and understand, even for people who don't have much experience. And they can even support OR-based logic, allowing multiple ways to prove the caller is authorized to invoke this function. Entities can be marked optional too. And while daiquiri is a proof of concept, I found that it saved me a couple of times from writing subtle vulnerabilities that would have gone unnoticed. If you get some time, I'd love for you to check it out and provide some feedback. Anyway, as we're wrapping up here, let's go over what we learned about today. First, we learned that typestates are a really powerful pattern to provide safe interfaces for developers. Second, we learned about the challenges in building software free from authorization issues, as well as strategies that organizations are using today to combat them. And lastly, we learned how to implement nonlinear typestates and how they can be used to model difficult problem spaces. My hope is that this talk has inspired you to explore solving unique challenges in your field by leveraging Rust's type system. Thank you for having me.